Thank you for your introduction. My name is Huajian. I'm working at Fraunhofer Institute in Germany. Today I would like to present our paper with the title YOLO-ICP, Deep Learning Integrated Post-Estimation for Bin pickings of Multiple Objects. So firstly, I will provide a brief introduction of the challenges in post-estimation and the background. Then I will introduce how neural network and ICP are integrated in our method. Next, I will present the result of the experiment and evaluations. Lastly, I will give you a short summary of this presentation. So let's get started with the background. 60 or 6 degrees of freedom post-estimation is important in robot manipulation, augmented reality. Traditional methods based on matching features or templates are widely used in industry, but they suffer from issues such as poor accuracy and low robustness when the object is textureless or when dealing with complicated things like multiple objects occluded by each other. In recent decades, deep learning methods have been widely developed. Post YOLO-60, for example, they use 2D or 3D images as input. Through the neural network, we can directly obtain the 6D pose as output. One major challenge we face is collecting training data, especially in industry projects. Typically, we can use equipment to collect the data, like motion tracking system, or we can manually match the template with the point cloud. But it is time-consuming and often inaccurate. So our objective of our project is to develop an AI-driven approach that enhances efficiency without requiring both labels. Now let's have a look at how our pipeline looks like. With the RGBD camera, we can get the RGB image and the point cloud of the scene. And we will train a neural network to segment each object. We choose YOLO-8 for this segmentation task because it's a now highly accurate, lightweight, and real-time object detection model and can be easily integrated in edge devices. Once we get the semantic mask, we will put it on the point cloud to get the point cloud of each object. Next step is to estimate the 6D pose of the object. To do that, we need to match the object point cloud with the template point cloud. As you can see, the camera can only capture the partial point cloud of the object from one direction. If we still use the entire CAD model for matching, that would result in deviations. Therefore, we decided to create a database containing local CAD point cloud from different viewpoints for matching. So we use Python library called Open3D to simulate virtual cameras surrounding the CAD model and capture the snapshots from different perspectives and extract visible points only facing to the virtual camera. In total, we use 8 perspectives, 4 from the upper and 4 from lower. This picture shows the result from the 4 upper virtual cameras. The first line displays snapshots of the CAD model from different perspectives, and the second line shows the depth map. Using this information, we can also generate the local point cloud facing towards the virtual camera. These point clouds will be stored in our database as template for matching. So in our pipeline, we use the point-to-point ICP registration algorithm for matching. It aligns 2 point clouds by iteratively minimizing the distance between corresponding points so that we could get 8 estimated poses for each object. Then we will calculate the root mean square root error to find the best estimated pose. We will choose the pose with the lowest error as the final output. So that's how our pipeline looks like. We also benchmark our pipeline on the open source dataset. It's called occluded Limon dataset. As the name suggests, it's a difficult dataset with occluded object in the image. It has more than 1,000 image frames with ground truth annotations. Each frame has RGB image, depth image, segmentation mask, and pose label. And 8 objects are to be should be detected in each image. It should be noted that two of them are symmetric objects that could impact the result of the different evaluation metrics due to the ambiguity in rotations. So we first train a YOLO network for object segmentation. During the training phase, all data is randomly split into training, validation, and test in a 7:2:1 ratio. And the training process started with a pre-trained model, which is based on the COCO dataset. After 300 epoch of training, the mean average precision reaches 97% on the validation dataset. With the completion of training, the model with the best performance will be deployed in our pipeline for segmentation. And the center of the detected point cloud will be used as the initial transformation metrics for post-estimation. So in order to evaluate the estimated pose of our method, we tested it on 200 frames. On this page, I will use translation error and rotation error to give an overview of the result. Translation error measures the positional difference between estimated pose and ground truth. As shown in the equation, we can use translation vector to calculate this error. A smaller translation error indicates that estimated pose is closer to the ground truth. In our result, we observed that 56.8% of the estimated pose have a translation error less than 20 millimeter. This shows that more than half our estimation are highly accurate in terms of positioning. And rotation error measures the angular difference between estimated and true orientations. In this chart, we can find that 32% of the rotation error are less than 10 degrees. On the other hand, over 10% of the estimated result have errors higher than 170 degrees. This is due to the symmetry of some objects which affect the result. And to compare our method with other algorithms, we use two standard metrics to benchmark its performance. The first one is called 2D reprojection error. This 2D reprojection error measures the average distance between 2D projections of the predicted pose and the ground truth. In our evaluation, a pose estimation is considered as correct when this average distance is below 5 pixels, so that we could calculate the accuracy in terms of 2D reprojection error. In this table, we compare our proposed approach against baseline models. As you can see in the last column, the mean accuracy of our method is the highest. Our approach demonstrates highly competitive performance comparable to the baseline models. We also measured the diameter of each object. We found that our pipeline is good at dealing with small objects. However, we do face some challenges with large objects. One possible reason is that we use the center of the cemented point cloud as the initial transformation matrix for the post-estimation. When large objects are occluded, the center of the detected point cloud may differ from the true center, leading to large errors during the post-estimation. We also evaluated the estimated pose in 3D space. We use ADD metric for asymmetric objects and ADDS metric for symmetric ones. ADD code average distance of model point measures the average distance between corresponding points in the predicted and ground truth poses in 3D space. For symmetric objects, directly matching corresponding points can be problematic due to the ambiguity in rotations. So we will use ADDS for the symmetric object. It calculates the minimal distance between each predicted point and the closest point in the ground truth model. And using these two formula, we can calculate the distance error in 3D space. when the error is less than 10% of the 3D model's diameter, we classify the result as correct. So this allows us to measure accuracy as shown in this table. The last column is the result of our method. Similar to the previous evaluation, this result shows that our method is competitive with baseline models, and our method achieved the second best mean accuracy with 38.9%. And moreover, our method shows better performance on symmetric objects comparing with other models. So in summary, we proposed a novel pipeline combined deep learning method with ICP. Our method integrated multi-view CAD point cloud database and does not require post-labeling. We also benchmarked this pipeline on the uploaded Limon dataset. The result shows that our method is competitive with the baseline models, and also it demonstrated strong performance on small objects and symmetric objects. And our research is funded by the Federal Ministry of Education and Research. That's all of my presentation. Thank you for your attention.